Okay, so in this video, we'll be solving an exercise about language operations and properties. This one is about language exponentiation and Cayley star, as well as their connection to like cardinality. So the question is, suppose we have an alphabet, which is just a singleton alphabet, so we only have zero. That's the possible symbol we can have. And we have a language over that alphabet, so it's a subset of sigma star. Then are the following statements true or false? And both of these statements are going to ask something about cardinality. So the first one is suppose L is finite. So the size of L is some integer m, right? Where m is greater or equal to 0. Then if we have some natural number n where n is greater or equal to 2, then it's saying that L power n, right? So the cardinality, or sorry, the cardinality of L power n is equal to the cardinality or the size of L power n, right? So in other words, it's saying that the size of this guy is m to the power n, okay? So this statement seems reasonable, mostly because it's kind of similar to a statement about the set product or the Cartesian product. So if I have A cross B, and the length of, or the size of A is n, and the size of B is m, then the size of this guy is going to be n times m, right? That's definitely true because we're creating tuples, right? We're creating tuples where the first element is from A, the second element is from B, and we're doing like a double for loop. So for every element in A, and for every element in B, um, add them as a tuple to A cross B. So, if we count the number of iterations that our double for loop does, then it's definitely n times n. So is the logic the same here? Well, I mean, it's definitely true if I have some language like L is, I don't know, 0 and uh, if I just have a language that's like a singleton, right? So if I have something like this, then it's definitely true that if I take sort of L power n, then that's going to be the language containing 0 power n, so that's just going to be 0 n. And so the cardinality of this, or the size of this, is going to be 1. And I mean the size of the language, the power n, well, that's going to be the size of the singleton, power n, so that's 1 to the n, which is 1. So it works here, right? But it's going to get a bit more tricky when we have more than one string. And the reason for that is because now we don't have this distinction of that we have in tuples where we have the first part of the tuple and the second part of the tuple. So let me show you what I mean. So if I have L is 0 and then 0, 0, right? And I have L squared, right? Then what is L squared going to be? So according to the statement, if it were true, then the size of L squared should be 2 power 2, so it should be 4. But let's see what happens if I actually compute this. So let me just make this a bit simpler and write 0 squared. Okay. So if I do the language concatenation, I take 0 with 0, so I get 0 square, 0 with 0 square, so I get 0, 0 square, 0 square with 0, so I get 0 square and 0, and then 0 square and 0 square. So the length of this set would be 4 if I would be distinguishing between 0, 0 square and 0 square 0, right? But actually, these two strings are the same, right? These two strings are both 0 cube, right? So because they're the same and because sets do not allow for duplicates, we would remove one of these duplicates and then we would get the set 0 square, 0 cubed, and then 0, 4, right? And so you see that there's a difference. There's a difference between the Cartesian product and the Cartesian product between the language and the concatenation between the language, where the Cartesian product, you can't like merge these guys together. But here, I mean, that's what you do when you have strings, right? When you have a first string and a second string, you merge them together to create a whole string, right? And so because we don't differentiate where the concatenation is here, these are the same strings, and so we get a set of size 3 rather than 4, right? So that's why the statement is false. So the statement is false because L squared, the size of L squared is 3, but the size of L power 2, well, that's 2 power 2, that's 4. And that's definitely not the same. Okay, so this first statement is false. What about this second statement? So the second statement says if L is finite, so again, let's just write it like this. If the length of L is equal to, or the size of L is m, where m is greater or equal to 0, then the cardinality of L star is the same as the cardinality of the natural numbers. So essentially, it's saying that we can create a bijection between the elements in L star and the set of natural numbers. Okay, so I'm going to show you again that this is, I mean, maybe at first, at a first glance, this seems plausible. So for instance, if I have L 0, L is like the singleton language that just contains 0. Then L star, well, that's just going to be a 0 power n, where n is at least 0. So it's at least 0 because L star also contains the empty string. And so then this thing definitely has the same cardinality as the natural numbers because we can create a bijection, right? We can say, well, the empty string maps to 1, 0 maps to 2, 0 square maps to 3, and so on. And so sure, there's like a shift, right? So the length here is 0, but then the number here is 1, but it's okay, right? We're still going to be matching all of the elements in L star to all of the elements in the natural numbers, and we're not going to do any sort of duplication. So we're not going to map to the same thing twice, right? So this is definitely a bijection. Okay, so it's definitely true in this case. But, and this is maybe a bit tricky if you don't see it, suppose L was the language that just contains the empty string. Okay, so this is a bit of a tricky question. So if L is just the language that contains the empty string, well, what is L star, right? Well, L star is, L naught, union L1, union L2, union L3, and so on. And then, this by definition is the language containing the empty string. This is just L, so it's the language containing the empty string. This is the language containing the empty string concatenated with itself. So then what we're going to get here is we're going to get something like epsilon square. But then epsilon square, that's like the empty string concatenated with itself twice. So that's actually just epsilon again, right? And then the same thing for L cubed. That's going to be epsilon concatenated with itself 3 times. But it's like I'm concatenating empty strings in Python 3 times, right? Well, that's going to just give me an empty string, right? So, so then this is also going to be empty, and for any n, it's still just going to be the empty string, right? It doesn't matter what the exponent is. So that means, right? That means that L star in this case is actually a singleton. So it's just the language containing the empty string, and so that means that this is false because for this to be true, then it would have to be true for every L. But it's not, right? Namely, if I have a counterexample here where if L is the language containing the empty string, then L star that has size 1, but then, the cardinality of the natural numbers, whether that's like aleph null or whatever, I mean, the cardinality of natural numbers is infinite, right? So this is strictly greater than 1. And so that's why this is false. So be aware of these like maybe tricky questions. I'll also ask you sort of as an exercise, what if I sort of disallow this edge case? So is the statement here, I'm sorry. So if I have a third statement, if L, the size of L is at least one, I mean, it's still finite, right? Then is this true, right? So try to see if you can come up with an answer. So I'll leave you guys on that.